get a little energy, guys. I need to, yeah, we have some amazing people talking. I don't want them to feel like they didn't get the energy they deserved. All right, thank you. Yeah, there we go, all right. So I'm super excited to introduce Florian Weisshardt. He's from Synapticon. They're building actuators, and they're really focusing on how to make the entire, to build safety into the entire robot frame. So I think I got that right. I probably didn't, but that's just me, and it's 3 in the afternoon. So please give Florian a big round of applause, and welcome to the stage. Thank you.
Perfect. Yes, thanks for the introduction, and welcome to my talk about, is there something to change slides? Oh, press. Thanks. Okay, so welcome again to my talk about humanoid safety. So in the next 15 to 20 minutes, I'd like to dive into what do we need to do to get humanoids out of the cage. So let's start to look at the different applications we see in humanoid robotics today, which is mostly entertainment, some security inspection. If we look into the near future, then there will be hopefully a lot more, covering logistics and manufacturing, but also hospitality and healthcare. And if we even look further ahead, there might even be humanoids in every home. And if you look from the left to right in that chart, we see rising need for AI capabilities. The cost criticality, of course, is higher, so cost needs to go down. And we also see more need for safety, because if you think of logistics and manufacturing, there might be restricted areas, there might be trained persons, there might be healthy adults standing upright on the floor. If you look at private homes, that might not be the case anymore and might be a completely different case. So there might just be a baby lying on the floor in front of the robot. And of course, that's a completely different safety case. But yeah, let's start with safety today, which is also, of course, needed for logistics and manufacturing and similar applications. So looking at some robot specs, what we typically see in humanoids today, from left to right again, with raising risk factors. So if you have a robot which is lightweight, it's not so much risky, then you would have a robot with more weight, more height, more speed of motions, more manipulation skills, probably also with direct interaction with humans, and that will all increase the risk so that a human gets injured by a robot. And of course, that's something which we all want to avoid. So let's take a step back. If we look at a robot, like an industrial robot, a mobile robot, if they are stopped, then we always consider them to be in a safe state. So whenever there is no motion in the actuators, no torque applied on the actuators, a brake being engaged, then those devices cannot move anymore. And that's typically also monitored with a safety system. And then humans are safe to approach. So whenever there is, you open up the cage, you press the red button, those systems will just stop, and then you can approach. But there are some products which are, where this stopped robot paradigm is not true anymore. So if you think of a car which goes 200 kilometers per hour on the left lane on a German highway, it's not the best idea to suddenly come to a stop. Because what you would do with that, you would even increase the safety case, because there might be people behind you which just continue driving and crashing into you. So the better safety action would be to move to the right side and slowly come to a stop. Same for an airplane, which is up in the air. So if you would have that plane stopped and there's no relative movement towards the air anymore, then there's no way for the airplane to just fall down even quicker. So also there, a stopped robot or a stopped airplane is not a safe state. And That's something similar we see also for humanoid robots. So if you consider a humanoid where you would just stop, meaning activate brakes in all the joints, then it's still an inverted pendulum, so it can fall any direction. And by that, it even increases the risk of an injury because it's a very uncontrolled fall. You don't know where it will going to fall, what body part will impact first on the ground, which direction. So that all those devices need different safety actions than just stopping. And compared to the industrial robotics, cobots, mobile robots, where a safe state is ensured with a safety system, we need a similar system on those cars, airplanes, and humanoid robots that reduce the frequency and also the effect of potential accidents. So what's the main safety challenges we see for humanoids? So in the very left side, we see a pure motion by a robot. That's nothing different than a mobile robot, a cobot, an industrial robot. So the robot is walking, moving arms, interacting with environments, objects, and humans, and by that, exposing a risk to a human. What you see in the middle video, which is a very old video back from 2015, the DARPA challenge, it's the instability of humanoid robots. So to any reason, if their control system goes crazy, if you unplug communication, if there's a power loss in a system, then there's no other way to fall for that robots. And today's robots, of course, do much better than in this 10 years old video, but the underlying principle is very much the same. So also if the AI system, the balancing system of today's humanoids fail, if you have a failure in communication, failure in power, then they will fall the very same way. The last thing, what we see as a safety challenges is the autonomy part, and that's true for all AI-controlled robots. Doesn't matter if it's a humanoid or another kind of robot, because if you compare that to traditional safety systems, again, for an industrial robot, at every point in time, you can derive from the programming what safety limits need to be enforced, so what a robot is supposed to do and what a robot is not supposed to do. And that's very different for AI-controlled robot systems because it's basically a black box and there's no direct relation between the video and language input and the actions the robot is doing on joint level, on Cartesian level, on the behavioral level. So also for that, it needs a different safety system to still claim a certain level of safety for those systems. So let's take a step back. What does functional safety mean? So functional safety is based on a machinery ISO norm and mainly focuses on risk assessment and risk reduction. So you typically start with categorizing the type of hazards you have in the system. Like you could have an impact with a robot, you could clamp your fingers. So you start listing all those hazards and then estimating the risk which comes from them, which is, for example, the likelihood of their occurrence, the frequency of the exposure, what's the degree of harm, so can you just get a scratch, or can you have breaking bones, or can you even have the head injured, up to death, of course, and also the number of persons being exposed to that. So, of course, a human robot is something similar not similar to a nuclear power plant, because if the humanoid robot fails, it's probably impacting like a single human or a group of humans, but not a full city or a full country compared to a nuclear power plant. But still, it's the same kind of methodology you would apply for that. And having all that estimated, you then calculate a hazard rating number, and based on that, you can get into a certain performance level and also derive additional measures you would have to apply to the system to reach a higher performance level. And the performance level in the end, that's just a measure of saying how likely is it that something fails in the system. So for performance level E safety systems, the mean time to failure is somewhere above 100 years. So it's very unlikely that something fails. And you typically achieve that by redundancy and diversity in the system, so that you have dual compute units, two ways of communication, comparing results, two encoder setups, so that everything is redundant and diverse. So that's exactly the principle which is used in industrial robots since decades. So if you press the red button, there's a safe torque off to the motors. There's probably a brake being engaged and monitored by the safety system. And most of the times, this is still hard circuitry, so electrical contacts which make up those safety systems. If we look at mobile robots and cobots, that's a step further. So there you have software-based safety systems which can take sensor input to make the robot stops. The mobile robot, for example, if it's in front of a person, in front of an obstacle, slow down its velocity and therefore react to persons and environments. Same for cobots. You might have them velocity limited, position limited, or even limited by force and torque on single axis and multi-axis level. So that's covering the safe motion part. So we can take that over for humanoid robots, of course. But still for the remaining two challenges, the instability and also the autonomy, there we need more advanced safety actions. And that's what Synapticon is working towards, also together with some big humanoid players, which will soon come out with safe humanoids to the market. So Synapticon is also participating in ISO standards, where there is no standard today for humanoid robots which you can apply. So you can take some parts of cobots, some parts of machinery, of course, some parts from mobile robots. But there is an ISO group about actively balanced or dynamically balanced systems, and we're shaping that. And by that also, we try to shape our product portfolio already so that we can later on comply to that standard. So that's the three parts which our positron solution is built on. So we have the safe motion part, which covers the risk of motion. We have the safe human detection part, which together with other systems can cover the instability of the robots. And then we have an AI behavioral safety part, which covers the autonomy part for AI-controlled robots. In the following slides, I'll dive deeper into that, starting with the safe motion part. So looking at the safe motion at a single axis, so no complete robot yet, just a single axis, we have typically this gray box, which is the motion control system, non-safe motion control system, which is responsible for executing a position, a velocity, a torque profile on the axis. And then, parallel to that, we have the yellow box, which is a safety monitoring system, which takes safety sensor inputs and is just monitoring what the non-safe motion control part is doing. And as long as this complies to certain safety limits in position, velocity, torque, then everything is good. If those limits are violated, then those safety system can kick in and, for example, take power from the motors, engage a brake, or in the case of humanoids, we have a principle of using safe dampers, where we, together with our drives, can, even in the case of there's no communication anymore and there's no power, we can shortcut motor phases and by that give different damping settings to the individual joints. I'll come back to that later, what kind of safety actions we can do with that. But let's first have a look at the next level safety systems. So we have the multi-axis level, where we do Cartesian movements, the AI system controlling the robot, and it's very similar. So we have a non-safe part, which has all the freedom as long as it complies to the safety rules, which the yellow block in this diagram, the safety system is monitoring. And that safety system is, for example, calculating a safe kinematics, so we know where the robot is going, how fast this is going, which height does the robot have, so it's standing upright, it's crouched, and then compare that with a safe human detection result, and again can then monitor safety zones, safety limits. If those are violated, we'll communicate that back to the single axis so they all know what to do. And in that case, it could be, for example, that front left of me, there's a human. And if there's no other way for the robot to fall, we can at least make it fall nicely, which means not fall towards the person, but fall back right. And how does it work? So we have our safe damper actuators. So we can, for example, make the left leg very stiff, the right leg very soft, and then give the robot a trend to fall to the right side. And we can achieve similar things if we have a difference in damping for hip and knee joints, for example, to let a robot crouch or fall forward and backward. So that decreases, again, the likelihood that the robot falls towards a person. And we have a safety-rated way of determining that, and that's making the robots much more safer than they are today without any features for letting the robot fall nicely. So coming to the safe human detection, how does that look like? So we have a camera-based setup where we typically work with different kind of sensors. So that could be time of flight, that could be color camera, that could be radar sensors, so that we have a performance level rated information about how many persons, which direction, which distance are persons. And then based on the ISO norms, there's different distances you have to keep. So for example, if a human can step towards a human, or can bend forward, can walk, or can stretch its arms, there's certain distances you have to keep from the robot. And that's all based on a ISO 10-18 formula, which takes into account the robot and the human-based movements and also uncertainties in the system, so that you can calculate a distance you have to monitor. And what we do is to extend that formula for humanoids with a fall zone. So that's the red part you see in the upper left image. That's basically what the area where the robot would fall on the floor. And of course, that's influenced by the robot height and speed. So a higher robot will have a larger fall field. A faster robot will have a longer fall field, but probably more towards a certain direction. So that will all shape the dimension and size of the safety fields, which is the yellow part in that image. And the yellow part is then the distance we have to keep to human. So whenever we have a human detection which is within that safety zone, we trigger a safety action. If that zone is not violated, we keep the non-safe AI-controlled robot going and just continue monitoring. And what's the kind of actions we can have? It's exactly what I just explained, that we can have different damping settings, let the robot fall, let the robot crouch, let the robot reduce its center of mass, reduce the velocity. So there's different actions we can do. Now to the last level, the AI behavioral safety. So in order to monitor the velocity limits and the position limits of the humanoid, we can't just apply a static factor to that, because that will change depending on what the robot does. And that's exactly what we monitor with the positron behavioral safety system. So in the upper left image, you, for example, can see that there's a human which just holds a model of a robot, which is categorized at not a dangerous situation, so everything good, we can go on. And the upper right image, you see that there's a sharp object pointing towards the person, so that's categorized as critically dangerous, and then that might apply more stricter position or even force limits, so that you can either continue or you have to stop. And yeah, how does that look in an overall system architecture view? So we have all the drives which report their safe position velocities. We calculate a safe kinematics out of that, so we know how fast the robot is going, how high the robot is. By that, we can select a safety case, like a larger or a shorter safety zone. We compare that with the safe human detection result, which comes through the camera inputs. and then can activate a safety action. And that loop continuously runs just in parallel to the AI control. So whenever the AI controlled robot is sticking to that safety limits, it's good. And the safety system will hopefully never get active, but it will be prepared and will get active as soon as those safety limits are violated. So thank you for your attention. And yeah, let's build safe humanoids together. If you're interested in more details, then pass by our booth. We're in the exhibition area, just the very last corner, but I guess you'll find us. Thanks a lot.
Thank you, Florian. We have room time for maybe one question, if it's a quick one. Does anyone have a quick question? Well, if you're holding on to it because it's not a quick question, make sure that you tackle Florian outside in one of our conversation areas because obviously there's a lot more to this conversation, and really appreciate your time. Thank you so much.
Thank you.
Yeah, I'll take that. And this guy, thank you.